Hi everybody. Let's look at how we can find the domain of different kinds of functions. So I got three examples here. The one on the left looks pretty simple, and the one on the right maybe looks fairly complicated. But really it's the exact same idea for all three of them. And that idea follows very directly from the idea of what does it mean to be the domain of a function. So we said before that the domain is the set of all input values for which the function is defined. So if we look at what function is happening on the outside of each of these, we see a square root. And we know that for a square root to be defined, if it's a real valued function, what's inside the square root has to be 0 or larger. Because if you have the square root of a negative, you end up with a complex number, which is a number with an imaginary component. So the example on the left, you probably already know. The domain is x greater than or equal to 0. If you prefer to use interval notation, you could do something like this. Oops. You could say the interval from 0 to infinity with a closed endpoint at 0 and an open endpoint at infinity. Okay, these other two look more complicated, but really it's the exact same idea. And here's the idea. If you have the square root of anything, then the domain of this expression, if you were going to treat it as a function, it must be the set of all numbers where whatever's under the square root has to be larger than or equal to 0. And it doesn't matter what we put in there. We know that the domain must be the values where that blob is larger than or equal to 0. So you can use that to set up an algebraic equation and solve for what the domain has to be. So in this example, what's underneath the square root is 2 minus 3x. So what we know is that 2 minus 3x must be greater than or equal to 0. And you can solve that to figure out what x values satisfy that condition. Same thing here. We know that 2 to the sine x must be greater than or equal to 0. And so you can solve that and figure out what x values must make that true. Go ahead and pause the video and make a guess on both of those or try and solve them, and I'll give you the answers. All right, for this one, I'll add 3x to both sides, and then I'll divide by 3 on both sides. So that gives me that x is less than or equal to 2/3, and that would be the domain of the g function. For this one, this is a little bit more interesting. If I was just going to try and mindlessly solve this using algebraic rules, it would feel like kind of a mess. So I'd have like sine x is greater than or equal to log base 2 of 0, and then I have to undo the sign, so it would be like inverse sine of log base 2 of 0, and now you're feeling sad, like what is that thing? But this is sort of a lesson in don't try and do math without thinking, because the answer here is actually very, very straightforward. You could think about this graphically or numerically. Numerically, we have that 2 to any power is automatically not even greater than or equal to, just greater than 0. Because you know that when you raise 2 to any power, it has to be larger than 0. So right away that you know that no matter what x value you plug in here, it will satisfy that inequality. So you don't need to do algebra. If you have several ways of thinking about your function and you can bring those different ideas to bear on any solution, you can often just jump to the solution. Graphically, you could think about it this way. You know that the function y equals 2 to the x looks like this. And that's just another way of seeing that no matter what the exponent on 2 is, the output is always larger than 0. So it doesn't matter if I have a sine x up here or what I have up here, because I know that whatever that number evaluates to be, 2 to that power has got to be positive. So don't need any algebra here. We can just immediately write x is all real numbers. Let's do a different set of examples. So we've got 1 over x, 1 over 2 minus 3x, and 1 over 2 to the sine x. So the exact same idea applies here. You probably knew the domain already of the function 1 over x, and the domain is just x can't equal 0, because 0 is the only input where 1 over x is not defined. So you can use that same idea for these other two. We know that whatever's in the denominator has to not equal 0. So in order for the function to be defined. So any x value that makes the denominator not 0 must be part of the domain. So just like last time, why don't you set up some equations and try and figure out what's the domain of h and g. Just like last time, I know that the denominator can't equal 0. So if I add 3x and divide by 2, I have that x is not equal to 2/3. Here, because of the discussion last time, I know that no matter what value I plug in for x, sine x is going to be between -1 and 1. And no matter what the exponent on 2 is, the output from 2 to that value has always got to be greater than 0. So it's not possible for the denominator to be equal to 0. Therefore, the domain has to be all real values. You can use those simple ideas in combination for more complex functions. So for this function, if I want to know what the domain is, I need to think about what are all the ways that f might not be defined. Well, it might not be defined if the denominator in this fraction is 0. But I've got this larger fraction also, so I have to make sure that this larger denominator is also not 0. And I also have a square root, so I also have to be sure that what's inside the square root is greater than or equal to 0. And then the domain would be any input that satisfies all of the requirements. So give this one a try. And here's the solution. So I know that what's under the square root has to be greater than or equal to 0. So I know that that has to be true. And so what that tells me is that x has to be less than or equal to 0. But that's not the full domain yet. That's just the requirement for producing a defined value out of the square root. The next thing we know is that the entire denominator here has to not equal 0. So that gives us the condition that 2 minus 1 over x doesn't equal 0. All right, so let's solve that one. I'll add 1 over x to both sides, so that gives me this. I'll multiply both sides by x and divide by 2, so that gives me x not equal to 1/2. So that is now another condition. I know that x has to be less than or equal to 0, but also not equal to 1/2. So last condition is I know x can't equal 0 because it's the denominator on 1 over x. So I know that 1 over x can't equal, I know that x can't equal 0 because it's in the denominator. So what do you get when you put all these things together? Well, I already know that x has to be 0 or negative, so I don't need to write this because this one is already implied by that one. I know that it's not 1/2 because I already know that it's not positive. However, this one says x could be negative or it could be 0, but this condition says that it also can't be 0. So if I put all three of these things together so that an x value has to satisfy all three of them, the final domain I end up getting is x has to be less than 0. X has to be negative. So you've seen a couple of problem-solving takeaways in this video. The first problem-solving takeaway is if you see a complicated problem, try and break it into parts. So that's what we did here. This looks complicated, but it's really just composed of several simple pieces that you've seen before. The other big one for me was not getting in a mode of just mindlessly following a process. I can program a computer to do that better than any human could. So what you want to do is focus on your human intuition. You got to use everything that you know about a function, or in particular, try and use the multiple representations idea of a function. So think about what would this thing be like numerically? What would it be like graphically? And that idea showed up when we were trying to consider what is 2 to the sine x. Realizing that you can think about that as 2 to the something, and 2 to the something is always positive, or if you imagine its graph, 2 to the something has a shape like this. So really making connections between all of your different ways of recognizing important features of functions, because you never know in a problem whether it's going to be easier to attack it algebraically, or to think about it numerically, or to think about it graphically. All right, good luck.